take a swig of your coffee, then let's head on over to our top secret code. So, we set up AddCon1 first with write justified output and using the full clock. We just set up the bits like we figured out using the datasheet. Then we head on over to AddCon0 and set it up using the bits we figured out from the datasheet. But notice that bit 1, the go done bit, we left it low for now. We'll set it high when we are ready to perform our conversion. All right, so next in our top secret code is all the setup stuff for the LCD display that we did before. Just copied and pasted from our previous project, which sets up the LCD for 4-bit mode, turns on the cursor, and all that stuff. The only thing I'd point out that's different is that when we send the bits to the display, notice that bit 4 on latch C is now our RS line. These are commands to the LCD, so I made sure that bit 4 is kept low during this setup time. We then get to our same routine which we had before, which called our message from the table and displayed it on the LCD display. Now you'll notice I've changed the message, is all I've done. I got rid of the second table and only wrote one line of text which reads analog read : on the first row of the display. So back to line 72. So you've seen all of this already, used it already and know how it works. We set the converter into action by setting the go bit high. The converter now starts to process its analog conversion. When we get to line 104, the label add check, this is where we get down to business. The converter is already running, working on its first conversion. So what we have to do is check the go done bit to see if the converter has finished and has cleared that bit to 0. We do that with a bit test. It's a bit test on a file. Skip the next instruction if clear on bit number 1. If it's still set high, it's not done yet, so we go back up to add check. We keep doing this until the converter is finished. When it clears the bit, we check and see that it's now cleared, and we skip line 106. We now skip the instruction and move on to grabbing the numbers from the buffer. Don't forget your bank select. Even if you're going to read a register, you need to select the bank. I know the bank selection is a bit of a pain, but as you'll see when we get to the Arduino, there's pros and cons to each system. So we select the bank for our low and high results, and we put those results into two GPRs. The low byte goes into GPR 78078, the high byte into GPR 079. Now, before we go on in our merry way to process the numbers that we just got, we go ahead and set the go bit high so the A to D converter can start working on its next conversion, which takes time, right? So we're going to take time to do all of our conversion, and so hopefully it will be done its conversion by the time we get back. So let's start it off running, and we'll go play with our numbers. We now get down to the complex process of converting our 2 bytes into ASCII characters, which we will send in 2 nibbles to the LCD. Okay, take a swig of your coffee. Before we get into the next mind-bending process, let's skip ahead a little and come back to this first nibble in a short while. Let's look at the second nibble first, because it's more complex. Scroll down to here, line 148 in my code. The first step is we load the lower byte into the W register, but we do so using the swap function. Now this, of course, swaps the upper and lower nibbles because we want to send the upper nibble first. The second thing we do is run the byte through an AND function, which removes the upper nibble. We then send a copy of the W register to another general purpose register, 07A. We're going to use that register to transfer the nibble to our math crunching subroutines. Now, this does not clear out the W register. So now we have two copies of this nibble, one in the 07A GPR and another copy still being held in the W register. In order to know what we need to do next, we need to determine if the nibble is a value of 9 or less, and so displayed as a single digit number, or if it's 10 or higher, it gets displayed as a letter. To check this, what we do is subtract whatever is in the W register from the number 9 and check to see if we get a negative result. So if the nibble in the W register is 10 or higher, so a hexadecimal A through F, we will get a negative result because 9 minus 10 equals -1, right? Now that's all we care about, because if we get a negative result, then the carry borrow bit on the status register will be set. That's easy to check with a bit test. So if the carry bit is set, we know that whatever number we got needs to be displayed as a letter. From there, we can deduce which offset value we need to add to the nibble to send it to the LCD display as an ASCII character. Get it? So, if the carry bit is set, that means the number is a 9 or less, and so we send it to a subroutine called ASCII prep low, which simply adds our lower offset to the nibble and sends it right back. It'll add the offset we figured out before, which is 0011 0000. If the carry bit is clear, that means the math result was negative, indicating that the nibble needs to display a letter. So it'll skip over this call command and instead call the ASCII prep high subroutine, which adds the offset to convert the nibble into an ASCII letter A through F. Now, before we go look at the subroutines, I just want you to notice and remember that when we call the ASCII prep low subroutine, when it comes back, it will immediately call the ASCII prep high subroutine. So let's see what happens there by scrolling down to the two subroutines. There. Starting here at line 208 in my code. Just look for the labels. So the ASCII prep low subroutine simply adds the offset we figured out earlier and then sends it back. It immediately sees the next line, of course, which calls the ASCII prep high subroutine. So it comes down here. We load up the W register with the byte, which is either a hexadecimal letter or in the lower nibble, or a number which has already been converted to ASCII in this previous subroutine. We do a quick check to see which it is. Now let's say it was a hexadecimal A, which is decimal 10. It skipped over the call to the ASCII prep low subroutine. So when the data gets transferred to here using GPR07A, you'll recall we deleted that upper nibble when we stored the number in that general purpose register. So if it was an A, that register will read 00001010. The upper 4 bits will all be zeros. However, if it has already been converted to an ASCII number, that means we added the offset of 0011 0000. The upper nibble will have some bits set. In fact, bits 4 and 5 will be set. So all we have to do is a quick bit test, which we do here at line 216. Now I used bit 5, but I could have used bit 4 just as well. If bit 5 is set high, that means it was already converted up here. We don't change anything. We send it right back to where it came from. If, however, the bit is not set high, that means the value is a hexadecimal A through F. So we skip the return command, add the needed offset to convert it into a letter, A through F, and send it back. Now, there's a whole bunch of ways you could do this, but this is one way, and the way I did it. If you don't like it, though, write your own code. Okay, let's head back up to where we called our subroutine, line 158. So now we have our number, which has been converted to an ASCII value, and we now send our 1 byte to the LCD display, 1 nibble at a time, just like we did before. Nothing you haven't already seen. We pull off a swap, putting our byte into the W register. With the nibble swapped around, we delete the upper nibble and then copy the upper level nibble over to latch C, putting it onto the pins of port C. Now, don't forget, bit 4 on port C needs to be set high because that's the RS line for the LCD display. So we set that high so the display knows this is a character we're sending, not a command. We then pulse the E line using the exact same pulse E subroutine we used before. We then load in the lower nibble. Send it out to the display in the exact same fashion, and voila, we've now converted our character to ASCII and sent it to the display. The cursor moves over 1, ready to receive the next character. After converting and writing all 3 characters to the display, we then pause for a moment. You can remove this if you want, but this just gives the display a second, actually about 0.8 seconds if you'll recall, to actually display the number. So the numbers will change at about 0.8 second intervals. It then goes right back to the start of the main routine. Checking to see if the A to D converter, checking the A to D converter to see if it's got our number for us. Okay, let's back up a minute here first. Back up to the first conversion, which is line 127 in my code. Because we're writing to our display left to right, we'll send the uppermost nibble first, then the second nibble, which is the highest nibble of the lower byte coming out of the A to D converter, then the third nibble, which is the lowest nibble of the lower byte. Because the number we're dealing with is only 10 bits, the upper byte has all zeros in the upper nibble. We can completely ignore that nibble. The lower nibble only has the lowest 2 bits. So the highest number it can send would be 3. So we can actually cheat and leave out a whole pile of this code because A, we don't need to check if it's a number or a letter. It'll never be higher than 3. And B, we don't need to delete the upper nibble. So here you can see I actually left all of that code in, though this isn't needed. We don't need to call ASCII prep high at all. We don't need to do a subtraction check and check the status bit. It doesn't hurt anything that we did, but we didn't need to. I could have just added the offset for our numbers, spit out the LCD, spit out to the LCD and 2 nibbles, and voila, we'd been on our first character. But where's the fun in that? So I left all of this code in there so you could see the process anyway. This was all very complex as it is, and I didn't want to confuse things. So build up your circuit, copy and paste the code into a project, and program your PIC. We did all of that just so we could see a direct readout from our PIC and the A to D converter. Now you can see here, I used a pot so I could get full swing from zeros through to 3FF, which is the highest number you can get in 10 bits. You can replace the pot with a thermistor and a resistor as a voltage divider, or your CDS cell. But now you can calibrate things because you know precisely what numbers the A to D converter is producing, depending on the condition of your sensors. All right, finish your coffee. You deserved it.